All right, here we go. The alternating series. This test is going to be easy, but we have to make sure that we meet the conditions, and really just meeting the conditions is the test, right? The integral test, you have the conditions, and then you actually need to do the integral. For the alternating series test, you really just have to check the conditions, and then that is essentially the test. But an alternating series is a series whose terms alternate between positive terms and negative terms. Duh, right? And there's really a couple different ways how we could get terms to alternate. We see this frequently. We see a -1 to some exponent, like -1 to the n+1. Or we could have something like -1 to the n. And then as that n, the index, as that changes, right? It starts at 1, then it goes to 2, then 3. As that n counts up by integer values, you'll have like -1 to the first, -1 to the second, which would be positive, then -1 to the third, which would be back to negative. And as that n counts up by integers, it's going to alternate between even number, odd number, even number, odd number. And we know that negative being raised to an odd power is going to stay odd, whereas that negative, every time it has an even exponent, will end up canceling. So when I have something like -1 to the n+1, or -1 to the n, when it's going to end up counting by 1, that exponent, the terms will alternate from positives to negative and vice versa. Doesn't matter whether it starts with a positive or whether it starts with a negative. That's irrelevant. What matters is it switches back and forth and alternates between positives and negatives. Be careful, something like this, something like that would not alternate, because no matter what you plug in for n, right, if your exponent is 2n, that exponent will always be even, right? 2n is how you could express an even number. So 2n would always be even. That means if I had a -1 to the 2n power, that one's just always going to end up being a positive one. But that one won't alternate, because that -1 to the 2n, that's just always going to be the positive output. Kind of similarly, if I had something like this, 2n+1, well, 2n is always going to give you an even number. And so therefore, if I take 2n+1, you know that exponent would always end up being an odd number. And if that exponent is always odd, your output will always be negative. It's not going to alternate between positives and negatives. It's going to always be the negative version. And that would work also if I had 2n -1. Both 2n+1 and 2n-1, those would always give you an odd exponent, right? 2n is even, but if you go up 1 from an even number or down 1 from an even number, that result is always going to end up being odd. And if your exponent's always odd, then the output is that term would always be a -1. So always look out for that negative in the parentheses and check out what the exponent is. If it's something like this, or if it's something like this, where the n is going to count by 1s, then yes, it's going to go even, odd, even, odd, even, odd, and then corresponding those outputs would be positive, negative, positive, negative. But if all of the exponents give you even numbers, or if all of the exponents always are odds, really they're counting by 2s, then that's not going to alternate. All of the outputs would either be positive or they'd be negative, and that's a problem, because we can't use the alternating series test if it's not an alternating series. Duh. Just like how we can't use the geometric series test unless it's geometric. Right? So always be careful and make sure that that exponent on that negative, it may not always be a -1. And we'll see an example today where I think we have a -2 in the parentheses. That negative in the parentheses, you need to make sure that exponent is going to actually cause it to alternate, and it won't always be one or the other. But here we go. This is the alternating series test. It says let us have some positive sequence, right? So a sub n is a positive sequence. Then it says the alternating series, so it takes that sequence and then it has that -1 to the n or the -1 to the n+1, right? That's really just going to make it alternate. So if I have an alternating series, which is just the summation of that positive sequence, but the -1 to the exponent makes it alternate, then that alternating series is going to converge if the following two conditions are met. The limit must be 0, and the next term, right? I always think about the a to the n, that's like the nth term, your current term, and then a to the n+1 subscript, that would be like the next term. So it says the limit has to be 0. That means, hey, those terms are going to get closer and closer and closer to 0. And then the ace of n plus 1 being less than ace of n basically means my next term is always smaller than the one before it. And really, those two statements kind of go together. But that statement 2, right, if your limit decreased and it just got closer and closer and closer to like 1, you could have those terms that are decreasing, and they could be decreasing and approaching a value of 1. But specifically, we need those terms to decrease in size or decrease in magnitude. But specifically, we know they have to decrease in magnitude and get closer and closer and closer to being 0. Okay, so really, here's a better way to think about those three conditions. Really, there's the 3 facts. It's got to be alternating. That's the first thing, right? It's got to be alternating. So my series must alternate in sign. That's the first thing you got to check. Because if it's not alternating, why are you using the alternating series test? Right? That would be silly. First condition, it's got to alternate. And the second and the third condition, they really kind of come together. But technically, the second condition is those terms have to decrease in magnitude. You can kind of ignore the negative or the positive. It doesn't matter. Magnitude just means size. And so when we're thinking about those terms decreasing magnitude, that means the next term is smaller than the one before it. So the 5th would be smaller than the 4th term. The 10th would be smaller than the 9th. The 100th smaller than the 99th, so on and so forth. You don't really need to do a whole lot to test that. But the terms have to decrease in magnitude. That means they get smaller in size as you write out that list, right? But specifically, they have to get smaller and they have to approach a value at 0. So these technically kind of go together, right? But the way that you can remember the alternating series test, there's really only these 3 things that you need to remember. They must alternate in sign, they must decrease in magnitude, and they have to have a limit that's equal to 0. And if you meet those 3 things, alternate in sign, check. Decrease in magnitude, check. Limit is equal to 0, check. If you get check, 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 you just know that that alternating series is going to converge. Now, if we are missing one of those conditions, right? So if we're somehow missing this one, right? If it doesn't alternate in sign, you can't say diverge. Like you don't know. This test only works and says if it's alternating, and if it's decreasing, and if it's specifically decreasing to 0, if all those things are true, then it converges. But if one of those 3 things doesn't work, then we don't necessarily know, right? The theorem only says if the things work, then it converges. We don't know what happens if one of those 3 things fails, right? So if the first condition fails, you can't use the alternating series test, but that should be obvious because if they don't alternate in sign, you can't use the alternating series test, right? So if the first condition fails, you're using the wrong test to begin with. And then really, if either of those fails, right, really the only work that we're going to have to do is we're going to have to take a limit, and we're going to have to make sure that that limit, as n goes towards infinity, that limit must be 0. But if that limit fails, if that limit is not 0, you don't say it's going to diverge by the alternating series test. No, remember, if the limit is not 0, then it actually is going to diverge by the nth term test. Okay, so if any of those 3 conditions fail, right, we shouldn't be using the alternating series test. Because if the first condition fails, then it's not alternating. Why are you using the alternating series test if it's not alternating, right? And then if either the second or the third one fails, really you should have just been using the nth term test to begin with. You don't need to even worry about the alternating series test. But if we do get that all 3 of those conditions are met, so the terms alternate in sign, which usually you just have to look at the series and then look, hey, do I have that -1 to the exponent, and is it gonna actually alternate? Or sometimes we have kind of some sneakier alternating things, and we'll see an example of that in a little bit. But if they alternate in sign, and if they decrease in magnitude, and specifically if they have that decreasing in magnitude where the limit is 0, if I get check, check, check for those 3 conditions, then I know, oops, I wanted to draw the arrow, not to erase it, oops. If I get check, 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 then we know that series will converge by the alternating series test. You can call it the Leibniz test also, but I think the alternating series test is the way that the AP exam is gonna call it. Okay, so it's really easy. 3 conditions: alternate in sign, decrease in magnitude, have a limit that's 0. If you get check, 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 there's nothing else you need to do. If you get check, 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 then that series converges by the alternating series test. If one of those 3 things is not a check, then that's a problem. Kind of, sort of. I have this little asterisk right here next to the second one, right? If the terms don't like uniformly decrease in magnitude, it's okay, right? If we're thinking about kind of like writing out what the terms would be, in general, we would want those terms to kind of look like this, where like as that list goes on and on and on, right, towards the infinitieth term, we're going to want that term, right, the size of that term, we want it to get really, really, really close to 0. If for some reason, if it starts off something like this, and then like if it gets a little bit bigger, and then it starts to decrease, it could work, right? It could still work, right? So it may not always be strictly decreasing. If there's a little part, specifically if it's kind of towards the beginning and early stages of that sequence, if we have that little spike where the terms actually get bigger for a little bit, but then you kind of get to this transition point, and then from that point on it's all decreasing, that's still going to be probably okay, because these terms that are increasing, really what we could do is we could kind of just break them off, and then I could just add what those couple of terms are, right? Since there's only going to be a handful of terms, I could just add them together, and that result's going to be finite. And then as long as the rest of this followed the alternating series test, like I could conclude, hey, if this, ignoring those things that are increasing, if that stuff, where they are decreasing, where they are alternating in sign, and where they have that limit that's 0, if that stuff's finite, then I could just add those other couple of chunks in, right? So technically, like we can actually kind of live if it's not strictly decreasing in magnitude. If you have that little spike where the terms get bigger, that's okay, as long as generally those terms eventually start to get small. If you have that spike towards the beginning, that's okay. You could just kind of break off those first couple of terms and kind of treat them separately from your series. And you think from that transition point, when they start to decrease, do they decrease and do they go to 0? And then if that part converges, once it starts to decrease, then you can take that finite result and then you could just add a couple of extra pieces from that initial spike. So that's why there's the asterisk next to the second thing, decrease in magnitude. Generally, that doesn't happen. The spike doesn't usually happen. But if it does, as long as it happens kind of early in that sequence, and then it still gets to some point where it eventually, right, as n goes towards infinity, eventually they get really, really, really close to 0, this test will still work. That's kind of a little FYI for you. You can technically get away with it when they're not always uniformly decreasing in size, but generally they're going to. All right, so let's go through some of these examples. Right, these are going to be pretty quick, pretty easy questions, and then we'll get into absolute versus conditional convergence, and then the error bound also. Here we go. First example. It says, determine whether the following series converge or diverge. Part A. Here we go. First thing I'm always going to check is, does it alternate in sign? Yes. Right? Because of that, it will alternate in sign. That's the first thing I always check. If I'm thinking about using the alternating series test, I'm going to check, does it alternate in sign? And there's really nothing you need to do. If you want to just circle that and be like, okay, cool, that's why, right? That -1 to the n plus 1, as that index changes from 1 to 2 to 3, that exponent is going to change from 2 to 3 to 4, and it's going to count by ones. Yes, that -1 chunk in the parentheses will cause it to alternate in sign. The next thing I would really check is what's the limit as n approaches infinity. There's really nothing you need to do to check for decrease in magnitude. If you wanted to actually plug in n equals 1, and then plug in n equals 2, and then n equals 3, if you wanted to like plug in some of those n values and actually look at the terms in that list, then you could kind of give it the eyeball test and be like, yes, the terms in that list, they actually do get smaller. If you turn them all into the decimals, it'd be easier to see that they're going to alternate from plus minus, or plus minus, whatever, right? But the size of the number, ignoring the negative if it's there, the sizes of those numbers will get smaller as you write out that list. But really, the only math you need to do is to check the limit. And then if that limit is 0, so you know the terms get smaller, right? Because they're going to have to approach 0. That means the terms themselves, right? 0 is literally the smallest magnitude there is. There's like 0 magnitude. So if the limit gives you 0, you really don't have to do anything extra to check and make sure that the terms alternate in sign, or the terms decrease in magnitude. So here we go. Let's check this limit. We've got the limit as n is approaching infinity. We're just going to take the limit of this general term. So here we go. We've got the -1 to the n plus 1, and then we have the n, and then we have the 2n minus 1. Now, really what we're going to do, just this once, and maybe on the next example too, but otherwise we probably won't split it up, is we're going to take this limit and we're going to separate it into really two different ones. We're going to take all of the outputs, right? Because this -1 to the n plus 1, that chunk will either give me a -1 or it will get me a +1. Right, so here we go. Let's just kind of think about the two extremes. We have the cases where the terms end up being negative. So I have a -1 and then n to the 2n minus 1. Those are all the collection of my negative terms. And then we have the collection of all of the positive terms, which would just be a +1n over 2n minus 1. So I kind of like collect all of the negative terms, and I'm going to check those. And then I collect all the positive terms, and I'm going to check those. Now let's look here. The degrees are the same, so that limit is going to end up being 1/2. And in that first one, the degrees are also 1, and so right, degrees are the same. So you look at the ratio of the coefficients. That limit ends up being -1/2. So let's think about this. Does -1/2 equal 0? No. Does +1/2 equal 0? No. So this limit was not equal to 0. So really, we didn't even need to worry about the alternatingness. Since the limit was not 0, we know my given series, I'm just going to say a sub n, right? That's all my a sub n. My given series diverges, but it doesn't diverge by the alternating series test. It diverges by the nth term test. If it were to fail the limit part, or if it were to fail really the decreasing in magnitude, it's going to diverge. But the reason why is because of the nth term test, right? So really the only work, right? We have the three conditions: alternate and sign. You just have to look at it and put a check. And then decrease in magnitude, really you just have to think about it and put a check or put an X. And then for the limit's the only one where we really have a work. So we're just going to take the limit, and then as long as that limit gives us 0, we're going to have check, check, check. And then we're going to say converges by the alternating series test. Right, but that one failed the limit condition. Since the limit was not 0, that series is going to end up diverging. So sorry, thanks for playing, but sorry, it doesn't work. All right, let's look at the next one. Here we go. We've got the summation from -1 to the n over n squared. So let's think, does this alternate in sign? Yes, right? That part right there is going to make it alternate in sign. Very good. And then let's check out the limit. We have the limit as n goes towards infinity. Now remember, that stuff in the purple circle, that's just either going to be a +1 or a -1. And that plus or minus 1, really, whether it's a positive or whether it's a negative, it really doesn't affect the limit that much. Okay, so here I'm going to have either a +1 over n squared or a -1. Instead of breaking it down and doing the two different limits, I'm just going to combine them, right? But as n goes towards infinity, right, infinity squared is infinity. If that denominator gets really, really, really big, then the fraction overall is going to get really, really, really small. The fact that the top was either a plus or a -1 doesn't matter, because the bottom goes towards infinity, which means, hey, that limit is going to be 0. So that's good for us. That's really the only work we needed to do besides thinking about the conditions. We should write, hey, it alternates in sign, check. It decreases in magnitude. You could also, if you wanted to do some work for this, you could think about comparing the nth term, right? It's either a plus or minus. Really, since it's just the magnitude, you really don't care if it's a plus or minus. If I think about the nth term compared to the n plus 1 term, right? If I'm comparing those two things and thinking about which one's bigger, because if I want them to decrease in magnitude, that means I would always want my next term with n plus 1, I would always want that to be smaller. So let's think about it. Here, the numerators are the same. Again, the plus or the minus doesn't matter because magnitude means size. We don't care. Absolute value, we don't care about the plus or the minus. But since that chunk on the right, since this has a larger denominator, we know that chunk overall would be the smaller fraction. And so yes, regardless of whatever n you plug in, the next term, n plus 1, will always be smaller. The denominator gets bigger, the fraction is going to be smaller. So if you wanted to do some work for decreasing in magnitude, really what you would do is you would just compare the nth term to that n plus 1th term, and then you could confirm, like, hey, yes, that next term with n plus 1 is going to be smaller, but you don't have to. When you do the limit, and if that limit ends up giving you 0, that's really all you need to do. But technically, the AP exam wants you to put alternate and sign, check. There's no other work you need to show for it. Right? Just look at the thing and make sure that it alternates. Alternating sign, check. Decrease in magnitude, you can just put check. There is work you can do for it, but you don't really have to. And then we take the limit as n goes towards infinity. That was 0, check. And as long as I get check, check, check. Now, this one should actually have work shown for it. The other two don't. But as long as I get check, 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 then I can say, therefore, my original series converges by the alternating series test. So there you go, right? All you need is just to worry about those three conditions, and if you get check, 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 your series is going to converge by the alternating series test. There is work you could do to alternate and sign to show that, but you really don't have to. Just look at it and confirm, yes, it's going to alternate, plus, minus, or minus, plus, minus, plus. It doesn't matter which one it starts as. But alternate and sign, just put a check as long as it does. And then really the work for the decrease in magnitude and the limit being 0, really all of that's kind of together by just doing the limit of the general term, and then you're good to go. All right, so as long as you get check, 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 converges by the alternating series test. It's a really easy test. You just have to remember what the three conditions are and then make sure you check them. If you fail the first condition, why are you using the alternating series test, right? If it doesn't alternate, you're not supposed to be using this test. And then if it fails either of the next two conditions, right? If it fails the limit, it's going to diverge. It's going to diverge because of the nth term test. All right, here we go. Let's kind of speed through this page of examples. These questions are pretty easy. I want to get you guys out of here pretty quick. But this page, let's just go through it pretty fast. Here we go. First thing we do, right, is always check. Does it alternate and sign? Yes. It does alternate and sign. That -1 to the n is what's going to do it. So then let's check. Is the limit going to be 0? Limit as n approaches infinity. Again, the plus or the -1, it doesn't really matter. We have the 3n over the 4n minus 1. Now the plus or the minus, that's cool, but I have the degree is 1 on the top, and then the degree is 1 on the bottom. So that limit would end up being 3/4, whether it's the positive or the negative. Right? The collection of all the positive terms goes towards 3/4. The collection of all the negative terms trend towards -3/4. And no, they don't perfectly cancel out. But since that limit is not 0, I know my given series diverges not by the alternating series test, right? If it says diverges and the limit's not 0, it diverges by the nth term test. Right, I know it's kind of weird. You're like, well, if the positive terms go towards 3/4 and the negative terms go towards -3/4, and my series is like adding them together, why don't they kind of cancel out? Well, if you're interested into the proof about this alternating series test, just go to YouTube it. I'm sure there's probably videos out there that kind of explains it. I'm not going to just for the sake of time. But if that limit is not 0, even if you have the positive one and the negative version, and you think they would kind of naturally cancel out, it's just not how it works. If that limit is not 0, then it's going to fail that condition, and then you cannot use this test. But if it fails that condition, really, it diverges by the nth term test. Kind of a little bit annoying, but ultimately pretty easy. Okay, let's look at the next one. Here we go. The -1 to the n plus 1, that's kind of fuzzy, but that will make it alternate and sign. Very good. And then let's check the limit. Limit as n goes towards infinity. Remember, that's just going to be plus or minus 1, so who cares? And then I've got the n squared over n cubed plus 1. Since the denominator is bigger than the numerator, right? If the degree on the bottom is bigger, this limit will end up being 0. Bottom is bigger, the asymptote is y equals 0, which is good. So here we go. We had alternate and sign. Visually, I could just look at it. The other two conditions, we needed to decrease in magnitude. Check. And then we needed the limit as n was approaching infinity. We needed that to be 0. And we did get check, check, check. Really, those two kind of go together with the limit work. And since I got check, 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 I could say, therefore, my given series converges, and always cite your test, by the alternating series test. So you just need to remember the three conditions. There's not a whole lot of math that goes into these. Alternate and sign, that one seems pretty obvious. Because if it doesn't alternate, why are you using the alternating series test? Like, that seems very obvious. And then you really just need to take that limit. If the limit is 0 and it alternates, that's good, converges by the alternating series test. If that limit is not 0, diverges, and it's actually going to diverge by the nth term test. You can look up proofs for that on your own if you're really interested, but it's not critically important, right? You just need to be able to answer the questions and know whether it converges or diverges. Here we go, next one. And this one's kind of the sneaky one because it doesn't have that negative inside of the parentheses being raised to a power, but instead it's actually got this, cosine of n pi. And remember, n is my index, it's going to be 1, then it would be 2, then it would be 3. Let's think about what cosine of n pi would be if we were to write it out. Right, so I'd have like cosine of 1 pi. 1 pi would be over here on the unit circle. Right, here's 1 pi, and the cosine of that value would be -1. And then we could have cosine of 2 pi. 2 pi would put us right there, and the cosine value would be a +1. What if I did cosine of 3 pi? Well, now 3 pi is going to be on the left, right? And so since I have cosine of n pi, and that n is just going to keep counting by integers, 1, 2, 3. Then it's just going to keep bouncing between the left and the right side of the unit circle, and the cosine of those points is just going to keep bouncing between -1 and +1, -1 and +1. So this one does alternate in sign, right? And it's not a -1 in a parenthesis that makes it. It's really that cosine thing that's going to make it alternate, right? That cosine of n pi ends up making it alternate between +1s and -1s based on your even and your odd n values. Kind of a little side note, if you had something like sine of n pi over 2, that would do the same thing. If you had a sine, you wouldn't want it to bounce left and right. If it was a sine, you'd want it to bounce from the top and the bottom, right? Because the sign at the top and the bottom, those are your plus and minus ones. So sine of n pi over 2 would also make it alternate between your positives and your negatives ones. All right, but that one does alternate in sign. And remember, this numerator, it looks ugly, but that numerator is either a +1 or it's a -1, right? So if we're thinking about it, right, the general term limit as n goes towards infinity, the top is either a plus or -1, and then the bottom is n. And then let's see, as that denominator goes towards infinity, that limit will be 0. So this one's going to work, right? It's gonna alternate in sign. It is going to decrease in magnitude. You don't really need to show any other work for that. And it does have the limit as n approaches infinity. It does have that limit equal to 0. And as long as you get check, 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 you can say, therefore, my series, again, you should probably name it like a sub n, therefore my series converges, and then cite it by the alternating series test. Pretty easy. For the integral test, you had to check, is it continuous? Is it positive? Is it decreasing? You had to have check, 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 and then you had to do something, right? Then you had to do the integral, the improper integral, to see if it converged or diverged, right? So you had to check the conditions before you could use the test, but really, checking the conditions for this alternating series test, checking the conditions is the test. There's nothing extra you have to do. It's a very nice, very easy rule. Here we go. Let's look at this last one, and then we'll move on. Here we go. We've got another summation. Now this denominator, if you wanted to, that's kind of ugly. That's like, it says n minus 1 is what that exponent is supposed to be. But I could really take this and I could split it up. And I could have the -1 to the n minus 1. And then I could have the 2 to the n minus 1. Right? Since I had a -2 inside of that parentheses, you could split it up. And then it's really, this is the piece that makes it alternate. Alternate in sign, yep. Because of that bottom left piece, oh my gosh, what did it just do? Whoa, come on, smartboard, what are you doing? Alternate in sign. And then we would just need to test the rest of it, right? That bottom left piece that's circled in orange, that's going to be the plus or the -1. So then really everything else is what we would need to check the limit for. So limit as n goes towards infinity, we have n over 2 to the n minus 1. And we're just really this one, like you could do work for it. You could do L'Hopital's rule, but really just think about relative growth rates. Which function would grow faster? The linear function x or the exponential function 2 to the n minus 1 or 2 to the x minus 1? Well, the exponential will grow much faster than the linear function. Right, so since the bottom grows faster, this one will be 0, right? This limit will get you to 0. The bottom gets to infinity first. L'Hopital's rule would prove it for you. I'm not going to bother at relative growth rates. we'll kind of get it at once. So alternate in sign, you could see that by that chunk. Yep. And then the last two, decrease in magnitude. We got that was a check. And then we did end up finding that the limit, as n went to infinity, that limit was 0. So we did get check, check, check. Therefore, my series converges by the alternating series, get out of there, test. So the alternating series test is actually one of the easier tests. A lot of these tests are pretty easy. The integral test is probably the hardest of them, but a lot of them are pretty darn simple. As long as it meets the conditions, that basically is the whole test. Does it alternate in sign? If not, why are you even using this test, right? Use one of the other 9. And if it doesn't alternate in, if it doesn't decrease in magnitude, or it doesn't have that limit that's 0, really that's failing the nth term test for divergence. So there you have the issue. But as long as you get check, 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 then it converges by the alternating series test. Right, so it's a pretty easy test. Just got to remember what the 3 conditions are. All right, let's move on to the next page. I'm trying to go quick, but also not too fast. Here we go. Where is my little arrow? There it is. Now, this is going to give us a little kind of small topic called absolute versus conditional convergence. And we're going to kind of highlight that by looking back at the harmonic series. Right? The harmonic series is your 1 over n, or really it's your summation, and that's your harmonic series. And if you remember, it was like a p-series test where the p equals 1, or you could use the integral test, but that harmonic series diverges. If you did the integral test, it's ln of n and the ln of infinity. Even though that natural log function is really, really, really slow growing, the natural log does end up going up to infinity. But that harmonic series, that was kind of the tipping point for our p-series test. That's where things started to be infinitely too big. And so that harmonic series diverges. The summation of 1 over n, starting with n equals 1 to infinity, that's the harmonic series, and it's going to diverge. You could do the integral test, you could do the p-series test, but really, if you just recognize it as the harmonic series, you don't have to do anything, because the harmonic series, you can just say, hey, that's the harmonic, therefore it diverges. You don't have to do any of the other 2 tests. That's just an accepted fact that you should know. But let's look at this other one that's called the alternating harmonic series. So these terms for the harmonic, they're like 1 plus 1/2 plus 1/3 plus 1/4, right? Plus dot, 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 right? The n just keeps getting bigger, right? That's what my harmonic series is. But what happens if we alternate? Right, like here, that -1 to the n minus 1. If I were to plug in n equals 1, let's see, 1 minus 1 would be 0, -1 to this. So it's going to start with a positive. So this one would be 1. Then it's going to end up being minus 1/2. Then it's going to be a plus 1/3. Then minus 1/4. Then plus dot, dot, dot. It's like the harmonic series, but half of the terms are negative. Because of that -1 to the n minus 1. And let's use the alternating series test on this alternating harmonic series. We know this one will alternate in sign, right? That -1 to the whatever power, that's what's going to guarantee it. Now let's look. Remember, the top is either a plus or minus 1. Let's take the limit as n goes towards infinity. The top is either a plus or a minus 1. But since that denominator is n, as n goes towards infinity, right, you're going to have plus or minus 1 over infinity. Oops, that's not infinity. That should be 0. So since the denominator gets really, really, really big, while the numerator is either a plus or minus 1, okay, that limit is going to be 0. So they do decrease in magnitude. Right? You could see that by writing them. Like that's 1, then it's 0.2, then it's, that's 0.5, then it's 0.33333, then it's your 0.25, then it would be 0.2, right? If you were to take all those terms and put them into the decimals, you could see that, yes, each decimal is smaller than the one before it, ignoring the pluses and the minuses. And we also did confirm that that limit, as n went to infinity, was 0. So the alternating harmonic series, that is going to end up converging. So that alternating harmonic series converges by the alternating series test. Right, so here we go. The alternating harmonic series converges, but the But the regular harmonic series, that one diverges. And by the way, you never really have to use the alternating series test again for this alternating harmonic series. You can just remember that harmonic diverges, but the alternating harmonic converges. You don't really have to cite a test for the harmonic, nor do you have to cite a test for the alternating harmonic. Those are just two really common sequences in series that come up, and you can just remember that the regular one diverges, but the alternating one converges. And let's kind of think about that, right? Like why? It's like a really fine line. Remember here, this summation, what we just kind of explained it was like this summation, right? As you were to have that infinitely long list of numbers, and if I were to add all of those list of numbers together, right, that infinite summation, for the harmonic series, when all of those terms are positive, that summation is infinite. Right? It's too big. It's not finite. Right? It's infinite. It's just barely infinite. But if I were to take some of these terms, right, and if I were to take some of those terms and then change them to minuses, then if I were to still take that infinitely long list, but with half of the numbers being negative, then that list is now summable. Because think about what happens if you change the signs for half of the terms. Instead of those things, right, think about the accumulation sum, right? Here for your regular harmonic, you're always adding in a little bit more, adding in a little bit more. Then the next term adds in a little bit more. But since those terms are always positive, you're always adding in a little bit more. And so my collective, my accumulation sum is just always going to keep getting bigger. But when half of the terms are negative, you end up losing value, right? You start off with 1, but then you lose 1/2. Now you gain a little bit back with the 1/3, but then you lose 1/4, and then you'll gain a little bit back, right? But since they alternate, you're not always adding stuff in, and that accumulation or that kind of cumulative sum, it's not always increasing, right? In fact, there's actually a bound for it, right? So when I change that list, so that instead of all of the terms being pluses, when half of those terms are now minuses, when it alternates, now that list, instead of it being an infinite sum, now that list is finite. So taking half of those terms and making them negative, right? All those terms, like 0.5 isn't big, 0.25 isn't big, but instead of having a plus 0.5, instead of having a plus 0.25, and then or whatever for the next couple of terms, right? When you change those pluses to minuses, that little flux, that swing from adding those small decimals to now subtracting those small decimals, that's enough to change you from the realm of an infinite sum into now just some finite number, right? But it's really because that harmonic series, it was like just barely infinite. That's like the tipping point for our integral test. It was just barely too big. If you think about kind of Goldilocks, I guess it's just barely too big, right? Because that one's infinite, but it's close. And in fact, it's so close that if I were to take some of those terms and make them negative, so that kind of whittles away and makes that collective sum smaller. If I take half those terms and make them negative, now instead of it being infinite, now it's finite. And that idea is what absolute versus conditional convergence means. If I have a series, it's going to be absolutely convergent if the regular thing converges and also the absolute value of it. So when all of the terms are positive, it converges, right? Absolutely convergent means it's like safely convergent. It's like safely finite. But if something is conditionally convergent, that means, yeah, it's finite. I could add all of those terms together, but if I were to take some of those terms and change them from negatives to positives, then it's going to end up being too big, right? So absolute convergence and conditional convergence, this is a little difference that we will need to know, right? Knowing whether something is convergent or divergent is nice, but also knowing what type of convergent is nice. Is it safely convergent? Like, is it solidly finite? Or is it conditional? Is it just barely living in that finite realm? The alternating harmonic series, that is a good textbook example of something that is conditionally convergent, right? That's 1 minus 1/2 plus 1/3 minus 1/4 plus ... right? As long as it's alternating, that infinitely long list is summable, right? The accumulation of all of those infinitely many terms, as long as half of them are negative, that's finite. However, if I were to take the absolute value of this, So if I were to look at just the harmonic series, and if those things that were negative, if those all got changed to pluses, like that's not a huge swing from going from a minus 0.5 to a plus 0.5, or a minus 0.25 to a plus 0.25. But if I were to take those negative terms and then make them all positive, now that infinitely long list, now it's not summable, because now that infinitely long list would be infinite, right? So something is conditionally convergent. If it's convergent, right, it's going to be finite, but it's like just barely under that threshold, right? If you think about kind of that fine line between things being finite and then things being infinite, right? Things that are conditional are like just barely finite. And those things that are conditional, if you were to make them a little bit bigger, right? So the absolute value of something, right, is if there's any negative, it's going to turn them positives. If you have something that's finite, but then when you make all the terms positive, if that is the tipping point that ends up making that collective sum infinite, well then, hey, it was like just barely finite to begin with. However, if I have something that's like solidly or absolutely convergent, right? I can add all those terms together with pluses and minuses, and it's finite. And if I were to even change the minuses and change those to pluses, which changing the minuses to the pluses makes that collective sum larger. But if I change the minuses to the pluses, but my result is still finite, that's what it would have meant to be absolutely convergent. Like it was like safely convergent because it was solidly finite enough that even when I make it bigger, by turning the negative stuff positive, even when I make it bigger, it's still finite. Okay, so that's the difference. Absolute convergence means, hey, the original series works and the absolute value of it also works. When I make it bigger, taking the absolute value of something either makes it the exact same, right? If my series is always positive, taking the absolute value doesn't do anything. But if that series originally was alternating, when I take the absolute value of it, it's going to make that collective sum larger, because now instead of having half of your terms negative, now all of them will be positive. So the absolute value is going to be larger. But if I take that absolute value and it's still finite, if it's still convergent, then we really could have characterized that initial as being absolutely convergent. However, if my original is convergent, but when I make it larger by taking the absolute value, if that changing the minuses to the pluses, if that's the thing that kind of tips you over the line and it moves you from finite into infinite, then you were originally convergent, but you were just barely convergent. You were conditionally convergent. All right, so absolute convergence, how to test it. Does the original work? Yeah, it's got to, because if the original doesn't work, then it's divergent and you're done. But if the original works and the absolute value of it also works, then that's absolutely convergent. It was like safely finite. However, conditional convergence is when the original works, but when you make it bigger by testing the absolute value, then it fails. Okay, kind of weird to explain. Hopefully that works a little bit. It's like solidly finite versus like just barely finite. It's kind of a weird little tipping point. We've got a couple of examples here. Determine whether the alternating series converges or diverges, and then if it converges, determine whether it's absolutely convergent or conditionally convergent. Okay, so always test the original. That's where we would want to start. Yes, this one is going to alternate in sign. The stuff that I circled is going to make that true. Let's check the limit. If I take the limit as n approaches infinity, remember the top is just going to be a plus or minus 1, and then here that's just going to be your root of n. As that n goes towards infinity, right, you're going to have plus or minus 1 over infinity, so that limit will be 0. Okay, so here we go. The original alternates in sign, check. It decreases in magnitude, check. Come on, check. And it has the limit as n approaches infinity that is equal to 0. Okay, so the original is going to work, right? So this original series from 1 to infinity, negative 1 to the n over the root of n. We know that one's convergent by the alternating series test. Okay, so the original is convergent, but we're going to figure out what type of convergent. Like, is it safely finite, or is it just barely finite? That's what the test for absolute convergence is going to tell us. All right, so now let's look at the absolute value of this sucker. And really, this test is easy, because remember the numerator, that's just either a positive 1 or a negative 1. So when you take the absolute value, basically it's just going to kill that negative. And And so here, oops, I don't want the limit yet. I want to have n equals 1 to infinity. The top is just always going to be positive. Because remember, when it alternates, it's either plus or minus, but if I take the absolute value, it's just always positive. And so here I would have the absolute value of my original series is just 1 over the root of n. You kind of just ignore that whole chunk, right? The top is just always 1 if you're always taking the positive. And that right there, that's P series. And that has the P series where the P is equal to 1/2. 1/2 is less than 1. And remember, that's the opposite of geometric. For geometric, less than 1 is converged. Therefore, for the P series, that means my new series, the absolute value diverges by the P series test. So the original worked, right? The original thing was finite. But if I make it bigger, and if I turn all of those negative terms positive, that's going to push it from being finite now into the realm of being infinite. So while the original converged, it was only conditionally convergent, conditional convergence. And how you know it was conditional is because when you make that series larger by turning all of the negative stuff positive, by taking the absolute value, now it's infinite. The original was finite, but it was like just barely finite because when I turned the negatives to pluses, when I made that stuff a little bit bigger, that pushed it into the realm of infinite. If that absolute value had also still worked, then it would have been absolute convergence. That's how you test it, right? It's really easy. You're going to have to just look at the original, decide if it converges or if it diverges. And if it converges, you look at kind of like the biggest version of that original. You just take the absolute value. And if the absolute value also converges, well, then your original was absolutely convergent. If that absolute value fails, though, then your original is only conditionally convergent. Okay, and again, the conditional convergence means like it was like finite, but it was like just barely finite. Whereas if something's absolutely convergent, like it's finite, but it's like safely finite. And even if I make it bigger, it's still going to end up being finite. Right? It's kind of the difference. It's the best way I can explain absolute versus conditional convergence. And I need to go faster because I'm running out of time. Here we go. Which of the following series is absolutely convergent? Okay, so let's go run through, right? This is actually 2 examples. We'll do the one on the left first, then we'll do the one on the right. Here we go. Let's look at the originals, and I'm just going to go quickly through it. This one's alternating. If you were to take the limit, right, you're going to have, since the bottom has ends, that limit will be 0. So that original is going to work, right? But if I were to take the absolute value of it, which means basically ignore that stuff, if I have 1 over 2n, or if you wanted to, you could factor that out, and you have just 1 over n, right? The 2 you could factor out. Ooh, look, that 1 over n, that's your harmonic. And we know the harmonic diverges. So here the original is going to work because of the alternating series test, but the absolute value of it is now going to fail because of because it's the harmonic series. So that one works initially but fails afterwards. So that one would be conditional convergence. Right, so that one's conditional. Sorry, that's not what we wanted though. We're looking for the one that's absolute. All right, let's look at the next one, B. That one's going to alternate. The n on the bottom means it's going to have a limit of 0. So yes, that one's going to work initially. If I were to ignore the negatives, let's think about it. Now it's that 1 over the root of n. Right, so now it's that P series with the P value equals 1/2, which is less than 1, which was going to diverge by the P series test. So that original works. But then the absolute value of it doesn't, right? That one was also conditional. That was the same exact example that we just did. Let's look at the C. It's going to alternate. But look, if you were to take the limit of this, right, that limit, as n goes towards infinity, that limit is 1, which is not 0. So that one diverges, right? That one cannot possibly be conditional or absolutely convergent because it diverges by the nth term test. Right? So we know by process of elimination it must be D, but let's just check it. Right? The original is going to alternate in sign. Yep. It's going to decrease in magnitude, and it has the limit. Right? Just check it as you have 1 to the n over 2 to the n. Since the bottom grows faster than the top, yep, that limit will be 0. Right? So that original is going to work by the alternating series test. But if I were to look at the absolute value of it, right here now it's geometric with the ratio that's 1/2. 1/2 is less than 1. Therefore, that absolute value of it, even when I take that original and I make it bigger by changing all the minuses to pluses, that absolute value is still going to converge by the geometric series test. So that one would have been like safely finite. It would have been absolutely convergent. The original worked, but then also when I make that original bigger by taking the absolute value, by turning the negative stuff positive, it still works. Therefore, it was absolutely convergent. Okay, let's look at the next one. Here we go. It's a multiple response question. The AP exam loves multiple response questions, right? 1 only, 1 and 2 only, 1 and 3 only, so on and so forth. Much harder than a regular multiple choice because you have options, right? Lots of different options that these could play out as. Let's look at this one. We know that's the alternating harmonic series. So I know that one's going to converge, right? That original is going to converge because it's the alternating harmonic series, which means the absolute value of it is the harmonic series, which is diverging, right? So that one works initially, but then fails. So I know that one is conditionally convergent. The alternating harmonic series is conditionally convergent because when I make the negative stuff positive, when I make it bigger, that pushes it from the realm of finite into the realm of infinite. Let's look at the next one. That one's going to alternate in sign. That one's going to decrease in magnitude, right? Since you have 1 over n cubed, that limit's going to work. So that one's going to work overall by the alternating series test. But if I were to compare it to this, or if I were to look at the absolute value, right, I'd have 1 over n cubed. That's a p series where the p value is 3. 3 is bigger than 1. So then that one is going to end up, that one's going to end up converging by the p-series test. All right, so this one's actually absolute convergence. First one was conditional, and the second one was absolute convergence. Right? It worked, and when I took the absolute value, when I made it bigger, turned all the negative stuff positive, it still worked. Okay, so that one was absolutely convergent. And then let's look at this last one, which, come on, I'm not going to do it again. We just did it, right? That one works initially, but then when I do it again, right, you get the p-series with the p equals 1/2, which is less than 1, which diverged. Right? We just did that one in the previous example and in the previous example, and it was conditionally convergent. Right? So which ones are conditionally convergent? It was 1 and 3. Absolute versus conditional convergence basically means how finite was it? Was it safely finite? So that if I make it a little bit bigger, if I change all the minuses to pluses, right, which makes your collective sum larger, if I do that, does that changing from the minuses to the pluses, does that keep it finite, right? Was it safely finite to begin with, so that even when I make it larger, it's still finite? Or was I just barely finite? And when I change the negatives to the positives, does that push it from the realm of the finite into the realm of the infinite? And when you were just barely finite, and the absolute value of it ends up diverging, because now it's infinite, that's really what you would call conditionally convergent. Right? So conditional versus absolute convergence, a little bit tricky, but hopefully not too bad. All right, now we got to just do this last page, and I know I'm taking up a long time. Sorry. Thank you guys for hanging in there for the async day, async quote unquote. We're just going to go through and we're going to do these 2 examples on this page, and then we'll be done. I know I'm basically taking the whole time today, but at least you can blow off the rest of your classes probably. Here we go. The alternating series remainder, aka the alternating series error bound. Let's read it. It says, if a series has terms that are alternating and decreasing magnitude and have a limit of 0, then the series converges. So we know, right? That's basically saying, hey, if you have a series that converges by the alternating series test, then we could have that infinite sum S, and we could approximate that infinite sum by using a partial sum. But a partial sum, only adding together the first n many terms, that partial sum is going to have an error. Right? All those terms past the nth term that you neglected, those are all the terms in my tail, and I want to know, if I were to add all the terms in my tail, all those unused terms in my collective, what's the biggest mistake I could have made with my approximation? By finding what's the biggest size that the collection of all the terms in the tail could have been. Right, so here we go. Then the error approximation, which the remainder a lot of the times you'll see with R sub n, that remainder, aka the error, is going to be less than the absolute value of the first, or the first omitted, or the first truncated terms. Okay, that's kind of a little bit weird, right? That the error, the maximum, oops, I don't want that. I wanted to, thought I had switched it over to the marker. the maximum error is going to be less than the absolute value of the first omitted term, right? So in other words, think about this. It says, if the three conditions are met, and you know it's going to converge by the alternating series test. Okay, very good. Then you can approximate what that infinite sum is by using the nth partial sum, but we're going to have an error, and that error is going to be bounded by the maximum mistake we could have possibly made is just the size of that first truncated or that very first term in the tail. Right? So let's think about something like this. Let's just go back to the alternating harmonic series just really quick. We had 1 plus 1/2 minus, I didn't want 1 plus, did I? I wanted minus. Minus 1/2 plus 1/3 minus 1/4 plus dot, dot, dot. Okay, now let's think about just, actually, I should probably do a little bit more. Here we go. 1/5 minus 1/6 plus 1/7 minus 1/8 plus dot, dot, dot. Okay, so let's think about this, right? That's my alternating harmonic series, right? It's got that, the infinite sum is all of the entire list. But we could approximate that infinite sum by doing a partial sum. Like if we did the third partial sum, right? There would be my approximation. And then all of these terms together, right? All those terms in the tail, if I were to add them all together, right? That's the biggest mistake we could have made, right? That's the size of all the stuff that we're omitting. But what we're going to say is that the collection of all of these terms is less than that first term was by itself. Right? And if you don't believe me, you could get a calculator, but I'm not going to get out a calculator because I'm already taking too long today. But just think about it. That first term is negative, right? So you've got like negative 0.25, right? If I were to add some stuff back, right, that 1/5, 0.2, that's less than 0.25. So I started off with this negative value, and then when I add in that second term, the positive and the negative, right, from these two terms, they're going to kind of cancel out. So that first term by itself had a size that was just 0.25. But if I were to collect those two, right, plus 0.2, now the size is just going to be 0.05. Now, the third term, if I were to add that one, right, now you're going to subtract a little bit. And I guess it would have been, yeah. So if I were to have the first term plus the second, which kind of whittles away since they cancel out, then if I were to minus, okay, now it's going to make that size a little bit bigger, and then add back to 1/7. Right? You guys see what's happening? Since they alternate, right, plus minus, they keep canceling out against itself. This thing by itself, the 0.25, the size of it, right, or really if you want to think about the negative sign, you will never, no matter how many terms in the tail that you get, you will never get a collection that's larger than the first term was by itself. And the whole key is because they alternate. Because they alternate, as soon as you get that second term, they're going to cancel out against each other. And the result of those first two terms added together, that size is less than the first one was by itself. Now, you could get that one and add some back. But even when I do all these three, all those back together, it's still not going to eclipse your 0.25 size. And then I could put in the next one, the 1/7, and then I could do the next one, right? And since they keep alternating, you're really going to be fighting a losing battle. It's like two steps. It's like one step forward, but two steps back. One step forward, but two steps back. One step forward. You know the deal, right? That first term by itself is larger. Right? It's negative, but that has a size that is larger than all of these terms combined. Even if that tail was infinitely long, that first term by itself is larger than the collection of all of them. Since they alternate, the positives and the negatives, they're going to cancel out against itself. And no matter how many terms in the tail that you add together, it will always be less than that first term is by itself. And that's all that this alternating series remainder is. Right? Whenever I make an approximation, right? Whenever I have a partial sum, it's going to have an error because you have all of those terms in the tail that you're omitting. But the first term in the tail, if you just look at that term, the size of it is bigger than all of the terms in the tail by themselves. So just the absolute value, the size of that first omitted term, that's all you need to look at. If I add the first 5 terms together, the maximum error is just the size of the 6th term, right? Just the 6th term by itself. If I add the first 10 terms together, right, that's my partial sum. All those terms starting with the 11th and then the 12th and the 13th, right, all those terms in the tail, if I added together, would be less than that 11th term by itself because they alternate, they cancel out against itself, right? If I add in many terms together for my partial sum, the maximum error I could ever possibly have is just the size of the n plus 1th term, the first term in the tail by itself. That's all you have to look at. That's the maximum size for your error. All right, so let's go for it. Let's do this example, then we'll try to speed through the next one, and then hopefully we'll get you guys out of here. Here we go. Approximate the sum of the series by using the first 4 terms. I'm going to write it out. And this is a factorial series, okay? I'm just going to write it out. Here we go. We've got, I'm just going to do it down here, actually. S, we can approximate it. The first term, actually, I'll just write it up here. We have 1 minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial plus 1 over 5 factorial minus 1 over 6 factorial plus dot, 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 right? That's what the series would look like if we actually expanded it. Now, here our partial sum, it says just the first 4 terms. So I'd have 1 minus 1 over 2 factorial, and then plus 1 over 3 factorial minus 1 over 4 factorial. And then you could leave it like this. If you wanted to change it, you could, or this would be like 1 minus 1/2 plus 1/6 minus 1 over 24, right? Those factorials up to 5 or 6 you probably should know, but if you were to add all those things together, it's going to end up giving you, right? Both of these things end up giving you 5/8, which if you wanted to convert it as a decimal would be 0.625. Okay, so there is my approximation, right? That's my 4th partial sum. You could say the 4th partial sum is, or you could say the infinite sum is going to be about. Right? But there we did. We added the first 4 terms together. We got 0.625. There we go. Part A, done, right? It's in the books. Part B says explain why the estimate differs by less than 1/100th. Okay, so here we go. Part B. By the alternating series error bound, I know my remainder, right? We did a 4th partial sum. So I'm going to look at just the size of that remainder from that 4th partial sum. I know my remainder is going to be less than the 5th term by itself. And it's really just going to be the size of the 5th term. So here we go. My remainder, I know is going to be less than that 5th term was by itself. What was that 5th term? It was this one, right? So it was the 1 over 5 factorial. Come on, that didn't get a very good factorial. 5 factorial. Since I added the first 4 terms together, I know, hey, like this is my partial sum, right? And so everything from this onwards, right? All that's the tail, that's the error. But this first term by itself is bigger than all of the tail combined. Because the terms alternate, they start canceling out against each other. So really, the first term by itself was the biggest that size of the tail was ever going to be. So all I need to do is look at that first omitted or unused term. And that's what my max error is going to be. Okay, that's going to be 1 over 5 to the 5 factorial is 120. And so I know my maximum error, the biggest mistake we could have possibly had by ignoring all of those terms in the 5th onwards, the maximum error is 1 over 120. Let's compare that to 1 over 100. Since 120 is bigger than 100, I know 1 over 120 is smaller than 1 over 100. Right, so there we go, right? We've proved it. Since we have the alternating series error bound, I know my maximum error is just the size, the absolute value. Even if it was a minus 1 over 5 factorial, we would ignore the negative. We don't care. I know the maximum error is just the size of that first unused term. The first term in the tail is bigger than all the terms in the tail combined. So if I just use that first term in the tail, that's your max error. But my max error, 1 over 120, it's less than 1 over 100. So there we go. We're good, right? We're actually more accurate than this. Since 120 is bigger than 100, 1 over 120 is less than 1/100. So we actually meet the required accuracy, right? Since 120 is bigger than 100, we meet the required accuracy. All you have to do is look at that first unused tail. Then here we go. Use our results to explain why. I'm going to get rid of this. Use our results to explain why the infinite sum S could not be equal to 0.7. Okay, now I'm gonna go take what this maximum error is, right? If you were to take that and type it into the decimal, you would get, well, I don't even have it written. Okay, but what I could do, right, I have that infinite summation, S. Now, if I were to take my partial sum, let's say, how about, which was, I guess, the 0.48. Let me just do it like this. There's the point, there's a 5/8. Okay, so we had the 5/8 and we had the 5/8. If I were to think about my maximum error, right, which was this, I don't have it as a decimal on my page, so I'm just going to have to use fractions. If I were to assume like worst case scenario, I could take my approximation and I could add in the biggest error. And I could also take my approximation and I could subtract the biggest error, right? In general, if I were to take my infinite sum, it's going to be bounded by my partial sum plus the max error and then the partial sum minus the max error, right? If I take my approximation, which is S of n, and if I add in the biggest whoopsies, and if I subtract the biggest oopsies, well, then that's going to give me this kind of window, this interval for where that true exact infinite sum could be. Right? If I take the approximation and I add in the max error, and if I take that approximation and I subtract the max error, that's going to give me this little window of where that true infinite sum could be. So here our approximation was 5/8. If I took 5/8 and I added in my biggest error size, I would end up getting 0.633, right? Those two, if you combine them, you'd get 0.633. If I were to take my approximation and subtract the biggest error, to kind of figure out the other extreme, what's the worst I could have gotten on that direction, it would be 0.617. So I know that real infinite summation, right, S, the infinitely long summation of the infinitely long list, I know it's going to have to live somewhere in between there. The 625, that was my estimation. And I know, hey, like this was my maximum potential error. So if I kind of assumed worst case scenario, if I took my approximation and I added in the biggest mistake or I subtracted the biggest mistake, that's going to give me this little interval of where that true function could lie. And so I know S cannot be 0.7 since 0.7 not in the interval. I'm running, get out of there. I can put that there. Not in the interval. Right, 0.7 is not in there, so therefore your infinite summation cannot be 0.7. I take my approximation and I kind of assume worst case scenario. I add in the max error and I subtract the max error. Right, that kind of gives you your wiggle room. That kind of tells you where that real thing has to lie. And since 0.7 is not in that interval, we know the infinite summation could not be 0.7. It could be something like 0.62. That would work. Or it could be something like 0.63. That could work. Or it could be 0.631, right? Anything in between 617 and 633. That could be the infinite summation. We don't know exactly. We could get it more accurate by doing more terms in the partial sum. But our estimation, if we always take the maximum error and add it, and then take the maximum error and subtract it from the estimation, that kind of gives us that little window for what that true function value or that true infinite summation could be. All right, I know, sorry I'm going so long today. I just got one more example and then we'll be done. I know, you guys are troopers. Thank you guys. Sorry it's going so long. This is a long lesson. Okay, here we go. Last one. It says, how many terms are needed to approximate the sum of the series so that the estimate differs by the actual sum differs from by less than 1/1,000. So this is kind of the opposite case, right? That previous question said, take the first 4 and then figure out what that maximum error was. But really, this one is kind of setting the specificity. It's kind of setting us, hey, you have to hit this specific accuracy, which means you have to figure out how many terms do I need in order for that next term to be less than 1/1,000. And how many terms do I need my partial sum to be in order to make this specific accuracy fit, right, in order to meet this criterion. And this is really what we kind of get into a lot in the next unit, right? Series are kind of nice, not because we really use them on their own, but we can actually take more really complicated functions and we could approximate them with series. But we know when I make an approximation, I'm going to have that element of error. And so I'm going to want to always make sure I hit my threshold, right? If we're building some kind of thing with an engineering kind of program or algorithm, right? If I'm building something, I need to make sure it hits my specs within a certain kind of range of credibility, right? Within this certain range of kind of acceptable error. So we have to figure out how many terms do I need so that my partial sum will hit that minimum or that maximum kind of amount of error, right? How many terms do I need? The last example told me 4 terms, and I had to figure out how big of a mistake could that have led to. Here, we're going to have to figure out how many terms do I need in order to guarantee that that mistake is going to be less than 1 over 1,000. So really what we're going to be doing is we're going to be writing out the terms in that list, and we're going to need to be making sure that we're going to find the term that is less than 1 over 1,000. And since, right, the top is either going to be a plus or a minus 1, right? So really I'm going to be looking for a denominator that is bigger than 1,000. Because if the denominator is bigger than 1,000, that means 1 over that thing would be less than 1 over 1,000. So let's just write out some terms. Let's write out some terms. Here we go. If I were to plug in n equals 1 or a equals 1, you would get 1. Then if I were to plug in 2 for the a value, you're going to have -1, 2 plus 1 is 3, so it's going to be a negative. So that one starts positive, then it's going to alternate. 2 to the 4th power is 16. Then if I were to take the third one, it's going to be positive. 3 to the 4th power is 81. Then if I were to look at the 4th term, 4 to the 4th power, it's going to be negative 256. And then I could look at the 5th term, which is going to be a positive, and then 5 to the 5th power is 625. See, I can't do the 4th partial sum. If I added the first 4 terms together, this would be my max error, but that max error is too big. Since that denominator is smaller than 1,000, that term is bigger than 1 over 1,000. So I need to keep going until I hit a denominator that's bigger than 1,000, right? And that will be my error term. But luckily, we only needed 1 more. If I were to look at the 6th term, which is -1 over, 6 to the 4th power would be 1296. Here we go. Since that denominator, right, this denominator is bigger than 1,000, that means this term is going to be less than, right? If you ignore the negative, that term is going to be less than 1 over 1,000. So that's my error term, right? If I were to add the first 5 terms together, right? If I were to add those first 5 terms together, I know my maximum error would be the 6th term by itself. So let's go ahead and write this out. For the 5th partial sum, you could also just say S of 5. For the 5th partial sum, the max error, right? So the maximum for that remainder for the 5th partial sum is less than the 6th term. So the maximum value for that 5th partial sum's error is going to be bounded by just the size of that 6th term by itself. Okay, so here we go. The maximum remainder less than, it's not less than or equal to, it's just less than, the absolute value of -1 over 1296. The negative doesn't matter, right? But since this is bigger than 1,000, I know that fraction overall is going to be less than 1 over 1,000. Right, so the 1296 term, the 1 over it, that was my error term. That means everything before it, the first 5, had to end up being my partial sum. So let's answer the question. How many terms are needed? Well, we would need 5 terms. If we, why did my M go away? 5 terms. If I only added the first 4 terms together, that means the 5th term would be the error. But that 5th term was too big. So I needed to go farther. If I went and did the first 5 terms, then the error would be the 6th term by itself. And since that 6th term has a denominator that's bigger than 1,000, I know that fraction overall is smaller than 1 over 1,000. Right? So I basically had to figure out which term is small enough to be my error term, and then everything before it will be the partial sum. Right? So for the 5th partial sum, S of 5, we know the maximum error would be less than the 6th term by itself. So I had to find what was that term that was the smallest size, which ended up being the 6th. So therefore 5 terms. And really your justification is like this. And if you wanted to say something like by alternating series error bound, it's always a good idea to cite your tests or to cite your theorems. right? By the alternating series error bound, I know that next term, that first unused term in the tail, that's the maximum oopsies we could have had from a partial sum. And since that sixth term was small enough, the first 5 terms needed to be my collective sum. All right, I'm really sorry that today took so long, especially for an asynchronous day. Thank you guys for hanging in there. You guys are free to go. Thank you guys. Keep working on the homework, get them turned in, and we'll have class again on Wednesday. See you guys.